talk a little bit about scientific notation, a way of representing numbers that's going to be useful for us in astronomy. If you're already comfortable with scientific notation, you know how to use your calculator to manipulate numbers represented in scientific notation, then just go right ahead, go ahead and calculate. That's all good. This is meant to be a review for people that haven't used scientific notation in a while or aren't familiar or comfortable with the ideas. We're going to need scientific notation because in astronomy we're always going to be dealing with numbers that are very, very big and numbers that are very, very small. And it just winds up being maddening to keep track of all of the decimal places if all I'm ever going to do is write out numbers in their decimal representation. Scientific notation also has the added benefit that it allows us to focus our mind on which digits in a given number are actually significant. So you don't wind up writing down an answer and handing it in that has 12 digits of precision when all the input numbers only had like 3 digits. Alright, so we'll start off with a number that may be familiar, written out in decimal form, which is by definition what the speed of light is, 299,792,458, and it's meters per second. We're not worrying about the units of measure at this point, just talking about a pure number. There's nothing that we're going to do in this class that's going to require that many digits of precision. There's really not many things in astronomy that are known to that precision. So the first thing I'm going to do is I'm going to rewrite this in a more convenient form. So I'll take it to be approximately 300 million, which is what it would round to, keeping 1, 2, 3 decimal places and then rounding from the 7 and the 792,000. So if that's what I'm going to be using in calculations, if I leave it in decimal form, that means I'm always going to have to keep writing out all of those placeholder zeros. And you know, maybe you're down with that. Maybe you really like your pen and your pencil and you like writing things over and over again. Let me give you another one. Another value. So 0. Which that is Newton's universal constant of gravitation if you write it out in decimal form. I need to have 10 zeros and then the first significant digit is a 6. That would really be crazy to use in a calculator or in arithmetic operations because all of these zeros, all 10 of them there, are just placeholders to tell you where that first significant digit actually is. And so in scientific notation, we are going to suppress all of those placeholder zeros by putting them as an exponent of 10 to some power. So writing numbers in scientific notation means I'm going to rewrite them in a form that's m times 10 to the n. So what are these? So m is called the significand. So it's a real number, and m is at least 1.0 and less than 10.0. So first part, it is definitely always called the significand. Older instances you might see it referred to as the mantissa. M is going to be, in general, a real number, And if we write it in our normal form, it's going to be at least 1 and then less than 10. If it was less than 1, that means we would shift the power of 10. And if it were bigger than 10, again, we would go back and shift the power of 10. All right, and then n is the exponent, and n is an integer. So m could be positive or negative, n could be positive or negative. All right, so let's go back and convert our x and y into scientific notation. There's our decimal point. So how many powers of 10 do we have? 1, 2, 3, 4, 5, 6, 7, 8. So in scientific notation, I would write this 3.0 times 10 to the 8th. Okay, so at least the 3 is significant. I'm going to write it so the 3 and the O are significant. And actually, if we go back to the rounding, this would be the same as 3.00. But I'm writing it with just 1 digit after the decimal point. Okay, and now let's try our y. 0.667. So what's the correct power of 10? So what's the exponent n? So I would be shifting the decimal point 1, 2, 3, 4, 6, 7, 8, 9, 10, 11 to put the decimal point there. So I'm shifting it 11 places to the right. So in scientific notation, this would be 6.67 times 10 to the minus 11. Okay. Let's talk about how we can do operations. If we want to multiply two numbers written in scientific notation. So for example, I have 3 times 10 to the 8th, and I want to multiply that by 2 times 10 to the 7th. So when I do this, the significance, I just multiply them together, and then the exponents add, because I have a 10 to the 8th multiplied by a 10 to the 7th is 10 to the 15th. So 3 times 2 is going to give me 6, and 8 plus 7 is 15. Very similar, if I'm dividing two numbers written in scientific notation, it's also going to be a similar pattern. I'm going to divide the significance, and I'm still going to add the exponents. But what you need to remember is that a number like 1 over 10 to the 3 is the same thing as 10 to the minus 3 power. Alright, so let's do a little division. We've got 1.5 times 10 to the 11th over, divided by 3 times 10 to the 8th. And what is that going to give us? Well, I need to divide the significance, so 1.5 divided by 3. And then I'm going to have one exponent is 11, and the other exponent is the denominator. So when I bring it up, it's going to be a minus 8. So this is going to give me 1.5 divided by 3. I'm going to have a times 10 to the 11th. I'm going to have times 10 to the minus 8. And what does that equal? 1.5 divided by 3 is going to give me 0.5 times 10 to the 11 plus minus 8 is 3. So we're not quite done yet because now I have a significand that is less than 1. So to put it in our sort of uniform way of writing things, I'm going to shift the decimal point 1 place, and I'm going to correspondingly change the exponent. So instead of being 0.5 times 10 to the 3, that's the same thing as 5 times 10 to the 2. All right. Talk about addition and subtraction. And admittedly, this is a little bit more awkward in scientific notation if you're going to do it with just pencil and paper. But of course, doing it with a calculator, it's no more different than multiplying or dividing. So if I'm adding numbers written in scientific notation, so let's say I wanted to do, we'll have a simple example first. 5.2 times 10, 10 to the 4th. And I want to add to that 2.2 times 10 to the 4th. Well, these already have the same power of 10. So this is straightforward. I just add the significance and I keep the same power of 10. So 5.2 plus 2.2, rumor has that as 7.4, and then times 10 to the 4th. And subtracting is going to go similar. We'll do one that's a little bit harder this time. 3.14 times 10 to the 4th, and I want to subtract 10 from that, which in our uniform way of writing would be 1.0 times 10 to the 1. That's 10. Okay. Now to subtract these, I'm going to have to pick one of the numbers and shift it until the exponents match. Okay. So I'm going to keep the first number the same, and I'm going to manipulate the exponent and the significand in the second number until the exponent is also 4. Then we can do the same thing that we did in the previous question, which in this case would just be to subtract the significance. All right, so I have to shift this until this is 10 to the 4th, which means I'm going to have to shift the decimal place over. So this would be 0.001, so I shifted it 3 places, times 10 to the 4th. Okay, so now my exponents match, so I can do the subtraction, But what we notice is there is no digit here that would even match that, right? I have this decimal place and then 2 after the decimal point. The 2 after the decimal point in the second number are zeros, and then I have the first significant digit. So my first number doesn't even have enough digits for this subtraction to be able to change it. I would need to know this to one additional decimal place past the decimal before I could subtract that 1 off from it. So that is also like one of the virtues of having numbers in scientific notation, is that it immediately tells you how significant another number is that you're including in an operation. Like if I'm adding a very small number or subtracting a very small number, it will have no effect. And if you wanted to have an effect, I would need to know the number that is being added or subtracted from to higher precision. All right, so that's addition and subtraction. You add or subtract the significance, but you can only do that once you have shifted the numbers, one of the numbers, until their exponents agree with each other. And the last thing we want to look at is exponentiation. So exponentiating a number written in scientific notation. So let's say what we wanted to do is square the number 500,000. So that's 5.0 times 10 to the 5th. And I want to square that. And so what do we do? We're going to square the significand. So I'm exponentiating the significand, and then we multiply exponents. So this is the same thing as 25 times 10 to the 10th. And now my significand is bigger than 10, so I need to shift it so I have it in our uniform form. So if I shift the decimal place over 1 to the left, I'm going to increment the exponent by 1. So 25 times 10 to the 10th is the same as 2.5 times 10 to the 11th. All right, and then another example of using this pattern of exponentiate the significand and then multiply exponents. Let's say we had the number 2.00 times 10 to the 8th, and we want to take the square root of that. So square root is the same meaning as raising to the half power. So this would give us the square root of 2.00. So I've exponentiated the significand, and now I multiply exponents. So that's going to give me a 10 to the 4th. And then the square root of 2 doesn't have an exact form, but it is approximately with 3 digits, 1.41 times 10